For this question, we want to use the graph of y equals 2 to the x and transformations to sketch the exponential function 2 to the x minus 5. We want to determine the domain and range, and also determine the y-intercept and find the equation of the horizontal asymptote. So we're going to start by sketching the graph of 2 to the x. We're going to do that by plotting points. I'm going to use a standard set of points that I typically start with. That's -2, -1, 0, 1, and 2. We'll substitute these into the equation y equals 2 to the x. And I'm going to start with the easy ones first. So let's start down here with an x value of 1. 2 to the first power would be 2. 2 to the second power would be 4. 2 to the 0 power is 1. Any number to the 0 power is 1, except for 0. We have 2 to the -1 power. When we have a negative in the exponent, we are going to do the reciprocal of the base. So to apply the negative, we need to have the reciprocal of the base. And then we'll still raise it to the first power, and that gives us 1/2. And we have 2 to the -2 power. The negative, we do the reciprocal of the base, and then raise the power to get 1/4. So that gives us a set of ordered pairs, and I'm going to graph this equation. We've got the ordered pair -2 1/4, -1 1/2, 0, 1, 1, 2, and 2, 4. So this is the sketch of our graph, our base graph, 2 to the x. And this function will get closer and closer to the x-axis without ever reaching it. We have a horizontal asymptote that is right on top of that x-axis. It's the equation y equals 0. And what we want to do is we want to use this basic function to graph this function here, f of x equals 2 to the x minus 5. So our function is f of x equals 2 to the x minus 5, and we want to use transformations to draw that graph. So what I notice is that I have one transformation, which is this -5. Because we are subtracting, this is going to be a shift. And that subtraction is in the exponent, and that makes it inside of the base function. And when an adding and subtracting is inside, that makes it a horizontal shift. Then we have a minus, so that means it's going to shift to the right. And we're subtracting 5, so we're going to shift right 5. So that means that all of the ordered pairs that I found on the graph of y equals 2 to the x will shift right to be on the graph of 2 to the x minus 5. So let's use a different color. How about this purple here? And I'm going to move each point to the right 5. So this point that is 2, 4, if I move that to the right 5, we will be at 7, 4. We have this point 1, 2, which will move to the right 5, and it'll be at 6, 2. 0, 1 will move to 5, 1. negative 1.5 will move to 4.5, and this point, negative 2.25 will move to positive 3.25. So this graph that has been shifted to the right 5 units is right here. F of x equals 2 to the x minus 5. And as I said before, the graph in black is y equals 2 to the x. And one of the things that you may need is those ordered pairs. So those ordered pairs on the new graph have shifted right 5, and you'll notice that the y values have stayed the same and only the x values have changed. So I'm going to extend my chart here, and I'm going to write down the ordered pairs that are on x, f of x. So on the original graph, we have the ordered pair negative 2.25. If we shift to the right 5, I am adding 5 to the x-coordinate, and that moved to 3.25. This ordered pair, negative 1.5, so we've already done this using the picture. I'm just using the ordered pair now. If we shift to the right 5, it's only affecting the x-coordinate. So I'm going to add 5 to the x-coordinate to get 4.5. The next point, 0, 1, we're going to shift that right 5. Right 5 only affects the x-coordinate, so I'm going to add 5 to the x-coordinate to get 5, 1. And then the next one is 1, 2. We're going to shift right 5 to become 6, 2. We have the point 2, 4. If we shift right 5, that will become 7, 4. So I want to make one more clarification before we answer the other parts of this problem. These ordered pairs in this column here are on the graph of f of x, and the ordered pairs that you see here are on the graph of the basic function 2 to the x. Okay, so let's continue. We want to make sure we find the domain and range. The domain of every exponential function is all real numbers from negative infinity to infinity. We can confirm that with our ruler. If we start on the left, this arrow here indicates that the graph continues on forever, so our domain starts at negative infinity. This arrow here means that the graph continues on to the right forever, and so our domain goes from negative infinity to infinity. Then we can hold our ruler horizontally to find the range, and you can see that on the bottom here there are no y values until we get to this horizontal asymptote at 0. So the range will start at 0 and will continue on to infinity. We have a range that starts at 0 and goes to infinity. We also want to determine the y-intercept and also the horizontal asymptote. So our original horizontal asymptote was at y equals 0, and you can see that because we didn't shift up or down, that horizontal asymptote didn't move. So the new horizontal asymptote will also be y equals 0. So finally, let's determine the y-intercept. You find a y-intercept by letting x equal 0. So in my function, I'll substitute a 0 to get 2 to the 0 minus 5 That's 2 to the negative 5th power, which is 1 over 32. So the y-intercept is 0 and 1/32. I think we've met all the parts there. On this question, we want to use the graph of y equals e to the x and the transformations to sketch the exponential function f of x equals negative e to the x plus 1 plus 2. Determine the domain and range, and also determine the y-intercept, and find the equation of the horizontal asymptote. The first thing we're going to start off with is sketching the graph of this basic function y equals e to the x. So I'm going to make a chart of x's and y's, and I'll use my standard set of x's, -2, -1, 0, 1, and 2. And we're going to substitute into the equation y equals e to the x. So let's start with the easy ones. E to the 1 is e, and that's approximately 2.718. Then we have e squared, and let's get a calculator out so that we can get some good approximations. We want to know what e squared is, and e squared is approximately 7.389. E to the 0 power will be 1. We can confirm that with the calculator. And we want to have e to the -1. And that's approximately 0.36. Let's use 8. And then e to the -2 is 0.135. So this gives us some ordered pairs that we can use to graph the basic function e to the x. We have -2 and 0.135, -1 and 0.368, 0, 1, 1 and 2.7, 2 and 7.3. So we can see a sketch of this graph. Y equals e to the x looks like this. It has a horizontal asymptote that is right on top of the x-axis, the equation y equals 0. And that's because this piece of the graph right here will continue to get closer and closer to 0. You can see that these y values are getting closer to 0 without ever reaching it. So then we want to sketch the graph f of x equals -e to the x plus 1 plus 2. The basic graph is e to the x, and we have a few different transformations. We have the negative, the plus 1, and the plus 2. The negative is a vertical reflection. The plus 1 is a horizontal shift. and that's going to go to the left 1. And the plus 2 is a vertical shift going up 2. So we're going to take the points that we had on the graph of e to the x and move them to their new position. So it's probably easiest to start with that point 0, 1. I think of that as sort of an anchor point of the graph because it's crossing through the y-axis. So from that position of 0, 1, we're going to shift to the left 1, would move to here. We're going to reflect vertically, so mirror over the x-axis, and then we're going to shift up 2. So you would get back to this point right here. Let's do that with 2 more points. I'm going to start with the point 1 and 2.7. We're going to shift to the left 1. We're going to mirror, reflect vertically, and then we'll shift up 2 and arrive at this position here. So it's a little bit hard to tell. I'm going to erase these intermediate points that I used. And let's use one more point. We'll start with this point here, -1 and 0.368. We're going to shift to the left 1. We're going to mirror over the x-axis and then shift up 2. And that would arrive here. So we've got these 3 points that seem to connect to each other, and it's a good idea to keep in mind where that horizontal asymptote might move to. The only one of these transformations that affects the horizontal asymptote is the vertical shift up 2. So the new horizontal asymptote will get shifted up 2 and will be the equation y equals 2. So now you can see that this portion of the graph will get closer to the horizontal asymptote, while this part of the graph will be mirrored. In the original graph, it was going towards infinity, and now in this reflected graph, it's going down to -infinity. So that graph in purple is the graph of f of x equal -e to the x plus 1 plus 2. It's also helpful to write the ordered pairs, the new ordered pairs. And I'm going to write a separate table this time for the x and the y, because the transformations affect both the x and the y values on this example. So let's highlight here. Using green, the transformations that affect the x are going to be the horizontal transformations. That's the one that shifted left 1. And in blue, I'll highlight the transformations that affect the y. The reflection, as well as shifting up 2, will be vertical transformations, and they affect the y-coordinate. So when we shift to the left 1, that affects the x-coordinate, and we're going to subtract 1 from the x's. So all of the x's will be subtracted by 1. So that makes -3, -2, -1, 0, and 1. For the y-coordinates, the reflection will make the y-coordinate opposite So when you're above, you mirror to be below. So all of our y-coordinates get multiplied by a negative, and then the vertical shift will add 2 to it. So all of our y-coordinates will get multiplied by a negative, and then we'll add 2 to them. So I started with this y-coordinate here, and I multiplied by a negative, and I added 2. And I'll do that for each y-coordinate. And we can type these values into the calculator to get approximations, and they should match with the ordered pairs that we've drawn on the picture. I have negative e to the negative 2 plus 2 would be 1.86. Negative e to the negative 1 plus 2 is 1.63. And negative e to the 0 plus 2 is 1. Sorry, I meant to write those down before I did that. So we have about 1.9, 1.6, and 1. And let's do the others. That should be negative e to the 1 plus 2. And that is negative 0.7. Negative e squared plus 2 is negative 5.4. So those should match up with how we shifted the points or transformed the points using the graph. And now we want to determine the domain and range. The domain of every exponential function is all real numbers, negative infinity to infinity. And I'm going to use my ruler to determine the range. So we're looking at the graph in purple right now, the transformed graph, and you can see that the range will start at negative infinity, and it will continue until we get to that horizontal asymptote of 2. So we have a range of negative infinity to 2. We also need to determine the y-intercept as well as the horizontal asymptote. We already mentioned that the horizontal asymptote gets shifted to y equals 2. And in this table that we have here, we already have the y-intercept. But if you didn't have the y-intercept, you would substitute a 0 in for x to get it. So we have the y-intercept being 0 and negative 0.7. On this question, we want to solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. The equation that we want to solve is 1 over e to the x equals the square root of e over e to the 2 minus x. The method that we're going to be using is called relating the bases, and as stated in the directions, we first want to rewrite the equation in this format. And the reason we want to rewrite it in this format, e to the u equals e to the v, is because exponential functions have this property called the one-to-one property, and it's allowing us to notice that these are y values, so we would consider this to be a y, and this is a y, and these y's are equal to each other because of the equal sign. And that one-to-one property says that if you have these y's that are equal, then these x's that are in the exponent must be equal, so u must equal v. So it allows you to simplify the exponential equation into some other type of equation. So we're going to start by trying to rewrite in this format, and we're going to have to use some properties of exponents. So one of the properties we're going to use is related to negative exponents. When you have a base raised to a negative power, you can get rid of that negative power by writing this as 1 over b to the n. That's because that negative means reciprocal. And also, if you have 1 over b to the n, you can bring that factor of b to the n to the numerator by putting a negative in the exponent. So that's what we're going to do with the left-hand side of this equation. So for 1 over e to the x, we'll write that as e to the negative x using the properties of negative exponents. The next thing we're going to do in the numerator is notice that we have a radical. And radicals can be written in exponent form. So anytime you have a radical, we'll say the nth root of something, then we can rewrite that as a power, and we're going to use the index, so that should be 1 over n. In a fractional power, we do that fractional power to indicate that we have a radical. So that's 1 over n. So for this example with square root of e, we can write that square root of e as e to the 1/2 power. In the denominator, I'll leave that alone for the moment. And then we're going to use another property of exponents called the quotient rule. And the quotient rule says that if you have a quotient, a fraction, and in the numerator and denominator you have expressions with the same base, so we'll say in the numerator we have b to the m, and in the denominator we have b to the n. So when you have division of exponents with the same base, what we do is subtract those exponents to simplify. So we are going to have b to the m minus n. That's exactly what we have over here. We have division, and we're dividing exponents with the same base. So we're going to simplify by subtracting those exponents. That will give e to the 1/2 minus 2 minus x. I put parentheses around the exponent in the denominator because I want to subtract that whole exponent. So we have finally gotten to the point where we have e to a power on one side and e to a power on the other side. And using this method of relating the bases, we're able to say that the exponent on the left, negative x, is equal to the exponent on the right, 1/2 minus 2 minus x. So we have now transformed this from an exponential equation into a linear equation. And I'll solve this equation. I'm going to start by using the distributive property on this negative. That gives negative x equals 1/2 minus 2 plus x. I don't like it when I have fractions in my problem, so the next thing I'll do is I'll multiply every term by 2 to clear out the fractions. That would give negative 2x equals 1 minus 4 plus 2x. That's what I get by multiplying by 2 on every term. And now I can combine like terms. I have negative 2x equals negative 3 plus 2x. I will subtract 2x on each side. And that will give negative 4x equals negative 3. Divide by negative 4 on both sides, and we have x equals 3/4. And x equals 3/4 is the solution to this equation. On this question, we have an application problem for exponential equations. It says typically weekly sales will drop off rather quickly after the end of an advertising campaign. This drop in sales is known as sales decay. Suppose that the gross sales S in hundreds of dollars of a certain product is given by the exponential function S of t equals 8,000 times 6 to the negative 0.9 t, where t is the number of weeks at the end of the campaign. Answer the following questions. What was the level of sales immediately after the end of the campaign when t equals 0? I'd also like to know what was the level of sales 1 week and also 5 weeks after the end of the campaign. So this function, S of t equals 8,000, 6 to the 0.9 t, is modeling the sales at a given time. So the first question is, what were the sales immediately after the end of the campaign when t equals 0? So we'll use our model with t equals 0 and get 8,000 times 6 to the negative 0.9 times 0. This is 8,000 times 6 to the 0 power. 6 to the 0 power is 1, and 8,000 times 1 is 8,000. So the sales are 8,000, and remember, our sales are in hundreds of dollars, so it's actually an additional 3 zeros on there, so we have a sales of 8 million at the end of the advertising campaign. And then if we want to find out what the sales were 1 week after the campaign ended, we're going to let t equal 1. since T is the number of weeks after the end of the campaign, so we'll find S of 1 to be 8,000 times 6 to the negative 0.9 times 1. And this one we're going to type in our calculator because it would be a little difficult otherwise. So we have 8,000 times 6 to the negative 0.9 times 1. So that's quite a steep drop off. We have 1,594.97. I think I added one too many zeros onto this one here. Hundreds, I should have added 2 zeros and not 3 zeros. So let me correct that. So that should be $800,000 in sales. And if I transform this into hundreds of dollars, that's going to be $159,497. And then if we want to find out what the level of sales are 5 weeks later, we're going to let T equal 5 and calculate S of T to be 8,000 times 6 to the negative 0.9 times 5. And I'll use this nice feature in my calculator. I can do second and hit enter, and that's going to give me the previous thing that I typed. And I'm going to go edit just that one number to be a 5. So this is quite a significant drop off. We have 2.52, which would translate to about $252 in sales 5 weeks later. We have another word problem in this example. An original investment of $14,000 earns 7.5% interest compounded continuously. What will the investment be worth in 1 year and also in 10 years? So as I read this problem, I noticed that the interest would be compounded continuously. And that indicated that I'd be using this formula for continuous compound interest. The formula is A equals P e to the RT. So I wanted to take a moment to go over what all of the variables stood for in this formula. The variable P stands for principal, or your initial investment. Then we have R, which is in the exponent, and R stands for the annual interest rate. T is also in the exponent, and that is our time in years. And we have one more variable, A, and A is the accrued amount, or the amount you would have after some period of time. There's one more letter in this equation, but it's not a variable. We have E, and E is approximately 2.718. It's a value that we even have programmed in our calculators. So I'm going to hit the second division button, which brings up E, and you can see that approximation of 2.718. This is a number very similar to pi that has come up when discussing exponential ideas, and so it is often used in formulas related to exponentials. So we'll use that value in our calculator once we work through the formula. So I'd like to read through the problem one more time to try to identify the numbers and what variables they stand for. An original investment of $14,000. An investment of $14,000 is referring to the principal or the initial investment. Initial or original. So P will be $14,000. If I continue on, this investment earns interest at 7.5% compounded continuously. This 7.5% refers to R, the interest rate. So R is 7.5%. In our formula, we don't use this value in percentage form. We're going to convert it to its decimal form. And you convert it to decimal form by moving the decimal point 2 places. Percent stands for per 100, and 2 decimal places are hundreds. So 0.075 is the value we'll use in the formula. We've already mentioned this information. Compounded continuously indicates which formula you'll be using. There is another formula which is called periodic compound interest, and that one you will see in the wording, it will say compounded monthly or daily or quarterly or some other statement besides continuously. What will the investment be worth in 1 year and also in 10 years? So we're given two values of time, t equals 1 and t equals 10. So we're going to have to use our formula twice to do those calculations. So now that I have all of my values, I'm going to substitute them into the formula A equals P e to the RT. We'll start with a time of 1 year. So A will be 14,000 times e to the 0.075 times t, which is 1. Let's type that into our calculator. We have 14,000 times e to the 0.075 times 1. And after 1 year, the $14,000 would grow to $15,090.38. I rounded to the nearest cent because we're dealing with money. Then I'll calculate the formula again using a time of 10 years. That's A equals 14,000. That was one too many zero. 14,000 e to the 0.075 times 10. I'm going to use a special feature of this calculator. I'll hit second and enter, and it'll take the previous entry that I typed, and I'm going to go in and edit that entry to change the time to 10 years. So after 10 years, an investment of $14,000 at 7.5% compounded continuously would grow to be $29,638.00. Thank you for checking out my videos. Have a great day.